Here's another example of vectors, which is easy, but you don't want to miss these points by being confused. Find the vector form of the equation of a line through this point A, 2, 1, 1, and the point B, 4, 0, 3. Notice they've given you Cartesian coordinates. Well, what does that mean? Well, it means from some origin O, we've got to go in the vector direction 2 in the x direction, 1 in the y, and 1 in the z direction. So from OA, that's what we do. OA is 2, 1, 1. And O to B is over 4 in the x, 0 in the y, and up 3. Well, we know that the vector form of the equation is R is equal to A plus lambda B, where that's going to be a point on our line. Well, then we can say x, y for this vector R is equal to the point on the line. The positional vector from 0 of this point is 2, 1, 1. So the vector is 2, 1, 1. Plus lambda. Now the key is, how do we find our directional vector B? It's parallel to this. It's going to be some proportion of this. So we need to know how to get that. Well, look, if this is our vector B is made up of going this way on A. So if A is normally going up from 0 to there, then the opposite of OA, which is here, the opposite of OA goes from A down, and then R goes this way. So we can find the vector from A to B is really the opposite of OA, which is AO, or we could say negative OA. We're coming down here, and then going up R, which is OB. So AB is the opposite of 2, 1, 1. I got that from here, plus 4, 0, 3. When I add those together, I get AB is 2, negative 1, 2. Well, that's this vector. I could just call it vector B. Or I can look and say, well, to go from 2 to 4, I have to go plus 2. To go from 1 to 0, I have to go minus 1. To go from 1 to 3, I have to go plus 2. This is our directional vector, which is our B here. And so this will be lambda times, in 3 dimensions, 2, negative 1, 2. And there's our answer. How did I find it again? Well, I know this picture by heart, that this vector R is made up of A and B. A is going to be here. It's going to be a point on the line. It's going to be the positional vector of a point on the line. And then I just have to find the directional vector rather. How do I do that? I can do the opposite of this plus this. The opposite of OA plus this. Or again, I can just think 2 to 4, 1 to 0, and 1 to 3. What's the difference? Find the acute angle between the straight lines. Well, they give us line 1, and here it is in Cartesian form, and line 2 also in Cartesian form. So let's take a look at line 1. Well, if x minus 3 divided by 2 equals y plus 2 divided by negative 1 equals z divided by the square root of 3, we can set all three of these equal to something else. Well, if they all equal each other, they must all equal something else. Let's call that something else lambda. So x minus 1 over 2 equals lambda. Y plus 2 over negative 1 equals lambda. Z over square root of 3 equals lambda. Well, if that's the case, if I'm looking at this equation here, I can multiply by 2 and add 3. And I get x is equal to 3 plus lambda times 2, which should be familiar to you as the parametric form. And then if I multiply by negative 1 and subtract negative 2, we get y equals negative 2 plus lambda times negative 1. If I multiply by the square root of 3, I get z equals, I put a 0 in there, plus lambda times the square root of 3. That should be the square root of 3 there. And so it should be there as well. Well, if I've got x is equal to this, y is equal to this, z is equal to this, I can now go to the vector form of the equation. X, y, z become x, y, z, which is our vector R. Our point is 3, negative 2, 0. That's our vector coordinates of the point. And then it's lambda times 2, negative 1, square root of 3, like this. So I've gone to the vector form by making each of these equal to some lambda, and then solving for x, solving for y, solving for z, and then sort of just making it in the vertical format. Here's my vector equation of line 1. Similarly, we can do the same thing with line 2. Instead of setting it equal to lambda, if this is equal to this is equal to this, I'm going to set them all equal to something else, which is t. So I'll set this equal to t, this equal to t, and this equal to t. Well, just as before, I'm going to solve for x, which means multiply by 1 and subtract 1 from both sides. Solve for y, multiply by 1 and add 2 to each side. Solve for z, multiply by the square root of 3 and add 1 to both sides. So I get my three parametric forms of the vector equation, which I'm going to take as x, y, z is equal to, well, here's my point A. The position vector point A is negative 1, 2, and 1, and then my the 1, 1, negative 3 will be my directional vector, and you see that there. So now I've got the second equation for the line 2, and I've got line 1 here. Once we find the vector forms of the lines, we know that what concerns us for the angle between us is the directional vector, here and here. These are going to be critical for helping us to determine the angle between them. We know that the dot product is A dot B equals the magnitude of A times the magnitude of B times cosine theta. We can solve for cosine theta. Cosine theta is, if you divide both by the magnitude of A times the magnitude of B, gives us the dot product divided by the magnitude of A times the magnitude of B. Well, the dot product of what? The dot product, this is critical, the dot product of the directional vectors, which will be x times x, 2 times 1, plus negative 1 times 1, y times y, plus negative 3, negative square root of 3, square root of 3 times square root of 3. All divided by, well, what's the magnitude of A? Use the Pythagorean theorem. 2 squared plus negative 1 squared plus the square root of 3 squared square root gives us the square root of 8. What's the magnitude of B? Well, use the Pythagorean theorem. 1 squared plus 1 squared plus square root of 3 squared, all in the square root is the square root of 5. 8 times 5 is 40, so that gives me the square root of 40. And on top, I simplified to 4. If I get cosine theta equals 4 over the square root of 40, I can solve for theta. Take arc cosine on both sides, or inverse cosine. I punch this in my calculator, I get to 3 significant figures, 50.8 degrees. That's the angle, the acute angle between these two lines. And what direction are these lines? The directional vector and the directional vector. That's the key component to put it into our formula here. Line L passes through the points 4, 3, 9, so it's in 3 dimensions, and 7, 8, 5. So I'll put that point A and point B, 4, 3, 9, and 7, 8, 5. Well, line M, here's line M, it passes through the points 12, 16, 4. Point A is 12, 16, 4 on line M, and point B is K, 26, negative 4. Notice, for our x value, we have a variable, 26 and negative 4. Well, we can see that this is a line and this is a line, so I can set it up in the vector form where I'm going from some origin, 0, 0, 0, and there's my vector R. Well, what is vector R? Vector R is some x1, y1, z1 will be equal to the position vector of A, which is 4, 3, 9, 4, 3, 9. Well, how did I find this directional vector? I did minus OA, so I went this way plus this one. If I take the negative of this plus this, then I really get 7 minus 4 is 3, 8 minus 3 is 5, 5 minus 9 is negative 4. I just got the directional vector from here to here. Similarly, this vector R is some x2, y2, z2, and how do you get that? Well, it's a point, or the position vector of a point, 12, 16, 4, there it is, x direction, y direction, z direction, plus some fraction or proportion or portion t times, well, this is the directional vector. It's k minus 12, 26 minus 16 is 10, and negative 4 minus 4 is negative 8. Or you can think of it as, here is OA, you can take AO, or negative OA, go this way, plus this. Either way, it gets you to the directional vector. Here is the vector form of this line, and here's the vector form of this line. What's most important? Our directional vectors. Remember that. Well, we've got our two, this is line L and this is line M, and we said that the directional vectors are the most important. Here's our key. If line M is parallel to line M, then our directional vector from line M will be equal to some constant m, that's small m, times our directional vector from line 2. In other words, x1, y1, z1 of our directional vector equals some constant times x2, y2, z2. Which means that x1 times m equals x2, and y1 equals m times y2, and z1 equals m times z2. That's what I meant right there. Well, solve for m. M is equal to x1 divided by x2, m is equal to y1 divided by y2, and m is equal to z1 divided by z2. Well, if m is equal to all three, then all three things are equal to each other. This is the absolute key for parallel lines. x1 over x2 equals y1 over y2 equals z1 over z2. For what? For our directional vectors. For our directional vectors. Again, here we are. x1 over x2 equals y1 over y2 equals z1 over z2 of the directional vectors if the lines are parallel. That just means 3 over k minus 12 is equal to 5 over 10 is equal to negative 4 over negative 8. You see, the concept is not that hard, and the math is very easy. Once you get this cross-multiply, 5 times k minus 12 is equal to 3 times 10, and then distribute and solve for k, you get k is equal to 18. The math is not hard at all. You just got to figure out what to do with this stuff. We're looking at directional vectors, and we know that this is true for parallel lines of their directional vectors. Well, part B asks, what happens if line L is perpendicular to line M? We find line L in vector form. We found line M in vector form. Well, this is critical. If line L is perpendicular to line M, then the directional vector dot product with the other directional vector equals 0. Well, how do you find the dot product? It's simply 3 times k minus 12 plus 5 times 10 plus negative 4 times negative 8 equals 0. You distribute it out, combine like terms, solve for k, you get k is equal to negative 46 over 3. Again, not a hard problem at all, but you just have to know first to put these in vector form, and then know that you're looking at here, you're just looking at the directional directional vectors. If the directional vectors are parallel, then you can set up the former proportion. If they're perpendicular, set up the dot product, which is equal to 0, and just plug and chug.